Welcome to Algebra. Today we are going to tackle a fundamental topic called row reduction and echelon forms. Imagine you have a massive, tangled ball of different colored yarns. If you try to pull one string, the whole thing knots up. You have to carefully untangle it one color at a time. In linear algebra, a matrix is often like that tangled ball of yarn, holding a messy system of equations. Today, we will learn the step-by-step process to untangle these matrices and reveal the clean, simple solutions hidden inside them. Now that we know our goal is to untangle these mathematical knots, let us understand what we are working with. A matrix is simply a rectangular grid of numbers. It represents a system of equations where all the variables are mixed together. Row reduction is our systematic step-by-step untangling process. We use it to clean up the matrix so we can easily see the solutions. By the end of this process, the matrix will look like a neat staircase where each step tells us exactly what one specific variable equals. Before we can build a neat staircase, we need to know what tools we are allowed to use. These tools are called elementary row operations. There are three simple rules we can apply without changing the underlying truth of the equations. First, we can swap any two rows, just like changing the order of equations on paper. Second, we can multiply an entire row by any non-zero number, like doubling a recipe. Third, we can add or subtract a multiple of one row from another. This third rule is our workhorse, allowing us to cancel out numbers and create zeros. With our tools in hand, our first major goal is to reach what is called row echelon form. The word echelon just means a step-like arrangement. A matrix is in this form if it follows a few strict rules. First, the first non-zero number from the left in any row is called a pivot. Second, every pivot must be strictly to the right of the pivot in the row above it, creating a descending staircase. Third, any row of all zeros goes to the bottom. Finally, all numbers directly below a pivot must be zero. Let us visualize this staircase shape to make it perfectly clear. What you are looking at is a matrix in row echelon form. Notice the asterisks which represent our pivots or leading entries. See how each pivot is further to the right than the one above it? This creates a clear descending staircase pattern, highlighted in blue. Below this staircase, every single entry is a zero. We have effectively cleared out the clutter below each mean number. This structure is what makes the system of equations much easier to solve. Sometimes, just having a staircase is not clean enough. We want the absolute simplest version of the matrix known as reduced row echelon form or RREF. This ultimate clean state follows all the regular echelon rules but adds two powerful new ones. First, every single pivot must be exactly the number 1. Second, the pivot must be the only non-zero number in its entire column. This means we must create zeros above the pivot as well as below it. When a matrix reaches this state, every variable is completely separated. Now that we understand the rules, let us convert a simple grid of numbers into reduced row echelon form. We start with matrix A, which has 2 rows and 3 columns. Our goal is to create a staircase of ones with zeros everywhere else in those columns. We work column by column from the left. The top left number is already a 1, serving as our first pivot. We need to eliminate the 3 directly below it. To do this, we take the second row and subtract 3 times the first row from it. Continuing our untangling process, our matrix now has a 0 below the first pivot. To reach reduced row echelon form, we must turn the second pivot, currently -2, into a positive one. We multiply the entire second row by -1/2. Now our second pivot is a perfect 1. The final step is to clear out the number 2 above this new pivot. We subtract 2 times the second row from the first row. The messy grid is completely untangled, leaving us with a perfect staircase of ones. Having seen the basic mechanics, let us apply this to a real problem, solving a full system of equations. When we have multiple equations with unknown variables like x, y, and z, we can write them as an augmented matrix. This is just a grid containing only the coefficients, which are the numbers attached to the variables, along with the answers on the right side. By transforming this augmented matrix into reduced row echelon form, we can reveal the exact numerical values of our variables. We must work methodically, column by column from left to right. Let us solve a system of three equations with three unknowns. We start with our augmented matrix. The first column represents x, the second y, the third z, and the fourth holds the constants. Our first pivot is the one in the top left corner. We need to make the 2 and the negative 1 below it into zeros. First, we subtract 2 times the first row from the second row. Next, we add the first row to the third row. The entire first column below the pivot is now completely cleared out. Moving to the second column, we need a new pivot in the second row. The current number is negative 3. But looking at the third row, we see a 3 and a 6, which are easy to divide. To make our math easier, we swap the second and third rows. This is a perfectly legal move. Now we can easily turn that 3 into a 1 by dividing the whole second row by 3. This creates a beautiful clean pivot of 1 in the middle of our staircase, ready for the next step. With our new pivot established, we must clear the number below it to continue building our staircase. The number in the third row is negative 3. We need to add 3 times the second row to the third row to cancel it out. This ensures the entire space below the second pivot is empty. Notice that our matrix is now in row echelon form. We have a perfect staircase of ones and a solid triangle of zeros below them. We could stop here, but we will push forward to reduced row echelon form. To reach reduced row echelon form, we must clear the numbers above the pivots as well. We start from the right side and work backwards. The third column has a pivot of 1 at the bottom. We subtract the third row from the first row to turn the 1 above it into a 0. Our third column is now perfectly isolated. Finally, we look at the second column. We subtract the second row from the first row to clear the space above the middle pivot. Every pivot is now exactly 1. We have reached the simplest possible state. This is our final reduced row echelon form, and the answers are staring right at us. Because we kept the columns organized by variable, we can read the answers directly from the right side. The first row tells us that 1x equals 1. The second row tells us that 1y equals 2. And the third row tells us that 1z equals 3. We have completely solved the messy system of equations without any guesswork, isolating each variable perfectly. Now that we have solved a system by hand, you might wonder where this is actually used. Row reduction is not just a classroom exercise. It is the fundamental engine that powers modern computation. Whenever a computer renders a 3D video game, it solves millions of linear equations using these exact principles to figure out lighting and shadows. In structural engineering, massive matrices are used to calculate the tension in every single steel beam of a bridge simultaneously. It is the ultimate tool for turning chaos into order in complex systems. We have covered a lot of ground today, so let us review the key takeaways. First, row reduction is a systematic method for simplifying a grid of numbers using 3 basic operations: swapping, multiplying, and adding rows. Second, our initial goal is row echelon form, which creates a neat staircase pattern. Finally, pushing further to reduced row echelon form isolates every variable completely, leaving us with a clean, obvious set of solutions. Mastering this process gives you the power to untangle almost any linear system you will ever encounter. Great job today.